My topic is hierarchical planning for autonomous excavator material loading task. My name is Liyang, Wang, and Zhixian and Liangjun Zhang are my colleagues. We are from Baidu, USA. Uh, excuse me. Okay. First, I'll give a brief introduction of the background and related work for this project. The motivation we do this is because there is a shortage for skilled laborers in heavy equipment operation. And a major challenge is general planning architecture for a wide range of tasks, which means there's no like very general planning architecture which can handle many different kind of tasks. And for this kind of research, there are several previous research papers. For example, Sue and Kim from South Korea has presented some high-level task level planning, and Hai and Bin has did some research on a single module for the like controller design and motion level generation. And there are some similar ideas in other machinery presented by Elizabeth. So this is our architecture of the entire planning. So first, let me introduce two concepts defined here. The first is called Material Removal Subtask Planner, we call it MRSP. And another one is Base Move Subtask Planner, called BMSP. We make this division is because in most general case, the excavator working are either moving the base using the track, or stay in the same position and just use the arm to dig or dump. So if we can separate these two kind of motions, it will be convenient to do to make the architecture more clear. So please see the figure on the left. First, the user interface will give this planner system the tasks it want to be. It could be a trench task, it could be a material loading task, can be different kind of tasks. Then there is a high-level task planner which will separate these the entire task into different subtasks. So it can first separate if this task needs to move base. If it has to move base, it can plan a task route point, different task route points, which means the excavators should stop at different places. And then it plans the material removal subtask, which is MRSP, which gives the task regions and goals. And there are they both plans for the MRSP. It plans the motion parameters such as dig motion and dump motion. And for BMSP, it plans the detailed waypoints. And then for the motion parameters, it will goes to the joint move primitives to plan the exactly trajectory. For example, if it's a dig motion, it will plan the exactly trajectory for the in the joint domain. And for the base move primitives, it will calculate the base trajectories. And then those trajectory goes to the controllers. We have joint controller to move the arm. We have base controller to move the base. And in the right-hand side, I list here the BMSP waypoints are defined in 2D cases currently. So the waypoints include three elements. One is X, Y in 2D, and the heading of the excavator. In the bottom figure is the walk zone defined for our MRSP. It can be sector definition, the rectangular definition. So the coordinate here, which is the in a BaseLink framework. So the origin, the BaseLink origin, we can see there's alpha, which is the swing angle. If the alpha is 0, which means the swing angle of the excavator is 0, and then the beta angle is the range of the area. And we have R max and R min, which is the length of this area. So we have 4 parameters can define a work zone for the MRSP. For next slides, which is a example of our high-level task planner. And then below, I will introduce 3 different kind of tasks, and let's see how the high-level task planner can divide into sub task problems. So the first is a trench task. For this figure, the trench begins on the left and ends on the right. And the green box is the entire trench task zone. And it has to be divided into subtasks. And we can see the red dot and blue dots here are the raw points. So the excavator space is stopped at the raw point 1, and the heading is to the left. And then the first MRSP subtask region is the region 1. So first we stop at the route 1 and move, dig in the region 1 and until the depth into the desired position, and then it drives back to the blue dot, which is the second route, and then do the same process and until finish the entire trench. So for between the 2 subtask regions, we also designed an overlap area, which makes the task more robust and done nicely. Then the second one is the power remove task. So it's also the green box is the entire regions, because the power remove task generally is wider than the trench. So here we use sector subtask regions, and this time it's the excavator moves forward. So it first stop at the raw point 1, which is in the bottom, and then work zone is the red sector, first the subtask region, and then push forward until the entire tasks are finished. And based on that, we also design large-scale power removal tasks. Suppose there is a very large scale, it can it should be have some sophisticated route planning to for the entire task. And we can see here the sector's angle is 180 degrees. However, we cannot in a real task, we cannot just set the task region 180 degree, because when the digging there will be some little base changes, and so we further separate a 180 degree sector into 6 small sectors. They also have overlaps to make sure it's fully covered. And also we will, based on our depths of the work, we can set the terrain into different layers. This, for example, for the sector 1, it has layer 1, 2, 3, 4. Actually, there will be set 4 different subtasks, and totally there is 6 multiplied by 4 is 24 subtasks for a 180 degree of sectors. And in the right hand side is the route planning. For the turn, we design a U-turn trajectory for the excavator to track, which can finish the entire task. And this is a detailed design for our MRSP. So there's first, we'll find the point of tag, which is a POA. Here is where the excavator bucket point will attack the terrain. And then we find the dig parameters. In the left figures, we see the parameters for a dig. The POAs has a position of X, Y, and Z. And then there are 3 phases, which is a penetration. It will penetrate depth is PD, and penetration length is PL. And then it goes to the drag phase. So the drag distance is DL. And then it closes the bucket to finish the dig. And sometimes the excavator is in a high place and dig downwards. So there could be an angle delta. make this make it see in the figures. And the right-hand side bottom figure is how the method we find the POA. We will first find the highest point in our work zone region and find the highest point and set an offset to find the right position for the point of attack. And in the algorithms, the procedure is first to set the subtask region and then set the subtask goal, which is the end condition. So we can set how what's the depth, how deep we want to clear this area. And then it goes to the loop to check if the end condition is met. If it doesn't meet, it will continue find the POA point and then plan for the dig motion and then plan for the dump motion. So we have different dump motion types. We can dump to the point, we can dump to the truck, we can dump to the actually desired positions. So we use the IK of the the trajectory optimization method for the dump motion. And then I will introduce our BMSB. So the excavator we modeled as the unicycle, as seen in the left in the right figure. So the two trucks are considered as two wheels, and we give the two truck force differently. For example, in this case, we make the right force larger than the left force, then the excavator turns left. So it's a unicycle model. And the end condition is the current position error and angle error are less than a tolerance. Then we consider our excavator has moved to the desired raw point. So then let me introduce our experiment setup. So in the real experiment, we use the XCMG 490DK model. And we use the Liangjun 100 LiDAR and RTK. And we also have the inclination sensor to detect the angles for each joint. We also have pressure sensors to calculate the stiffness of the materials we are working with. So the sensor's positioning frequency is 10 Hertz. And the joint angle frequency is 100 Hertz, and the point cloud is also is 10 Hertz. So this figure shows our experiment for the trench. We defined the trench entire region is 10 meters by 1.5 meters and 2 meters. And in the figure, in the image left is the before the trenching, and in the image right is after the trench is done, which you can see the trench is done nicely with the desired shape. And this is the experiment of our pile remove task. So the pile in front is 8 meters long and 0.5 meters high and 5.6 meters wide. And as we use the pile remove task planner to separate into the sectors, we can see in the bottom, which is the figure from the software. We can see the right box is the entire task zone, and the yellow sector is a subtask zone. And after that, the power has been completely removed. And we also did our large-scale power remove experiment in the simulation environment. Because it's very hard to do in the real world currently. The excavator we used is the CAT 365CL model, and the simulation environment we used are AGX, which gives the dynamics of the environment. It also have the model for the soils. So in the right figures, the setup is we set a pile, the squared area, which we can see the color is slightly different, which means the height of the terrain is higher than others. So the excavator start from the right box, and it first plan the route and goes to the first raw point, which is the white dot. in the bottom left figure, and then it start to first remove the right hand side and push forward, and then it perform that U-turn and then walk on the left hand side of the terrains, and finally it completely remove the entire soil. You can see in the right top figure because there is no truck or something to carry on the soil, so we can see the piles after dig is like that, but the entire original soils are completely removed and the color are same to the background.
Sorry to interrupt. 1 minute. Oh, yeah.
So actually, then now we go to our conclusion. So we present a novel autonomous excavator planning system. This planning system are general, which can handle different kind of excavation tasks. In the future, we will work on more different kind of tasks, such as surfacing and surfacing the ground in the constructions, and we'll extend our base move planning with 3D assumptions. Currently, we assume the raw point is in 2D, and then we'll along with balancing the feature of uneven terrains. Okay, thank you very much.